Today we have Daniil speaking about local relative Langlands conjecture.
Nice to meet you. Nice to meet you. Yes, so today's topic is so there is a more general topic of relative Langlands conjectures that tell about different categories attached to pair of group and hyperspherical variety that I will tell more about later, and Langlands dual group and dual spherical variety. Today we are discussing one of these conjectures, namely local unramified relative Langlands conjecture, and I will formulate it in at some point. So let me just start with setup. I will not say much about this extension of correspondence to hyperspherical varieties. I will not define hyperspherical varieties. I will just, so the only example that we will need, and the only example that is precisely defined in the conjecture that we will discuss is of the case when M is just T star X, where G acts on X. X is spherical, meaning there is open B orbit, and so just because of T star, we have moment map that we will not use at all on this side. So we have moment map from M to G star to the algebra, and on so yeah. So excellent. Yeah, so like we will not discuss much the one side, just that okay, we have T star X, and in some examples I will say more about some more general examples of hyperspherical varieties, but I will not give details. So mostly we will be working with this case, and the only thing that we will discuss a lot about dual case is just there is a moment map on dual side. So we have from check to G check star, and that's everything that we will need today. Also, we will need grading action. So there is a multiplicative grading group that acts on M check scale. So there is some description of this action available in the article. We will not use it also at all, just that moment map is equivariant with respect to this grading action, where the check star has weight minus just as weight. So this grading action scales symplectic form as we usually require, and so it follows that check has weight 2, then this moment map is equivariant with respect to grading action, and it's kind of all use setup. And there are several examples of dual pairs of assignment of M check to M, and there is a general procedure described in paper. And mostly I will use one example, very simple, where X is just A1, G is GM. And in this case, kind of nothing changes. So M check is T star A1. So both M and M check are T star A1, and both G and G check are GM. With GM acting naturally on A1. Any questions about that? Yeah.
And also, and Mr. And check.
It's something. It's some variety. It's some variety with Hamiltonian G action with a moment map. So action of G check on G check is I guess I should have said that. So M is symplectic, so M check will also be M check is also symplectic. And this U is moment action of G check on M check is Hamiltonian. And that's all. Okay, so I will say even less about categories of sheaves. So as usually happens in this business, there are constructible sheaves on one side and coherent sheaves on the other side. And constructible sheaves come in many flavors that I will not discuss at all. Just that, notation. So we use capital letters to discuss large category. Complete. And just CHV to describe small category. So in usual cases, this will be directly generated, and this will be in completion small. So we will not use any technical definitions or properties or at all, just that there are two sizes of constructible sheaves and two sizes of coherent sheaves that I will also describe when formulating the theorems. And there are also three flavors of constructible sheaves that appear a lot in paper, but we will not discuss it that much. So there are Betty and Etal. And I will not discuss Betty at all. The RAM is like D-module, so everything is over complex numbers or constructible sheaves, and Etal is melodic sheaves. So on one side, the field will be the field over which M and G are G, M here, C here as F bar, and coefficient field C and Q bar. And G check and M check are defined over this coefficient field. So I will mostly, you can mostly think about C and we will not discuss things on the level of details where it matters. Just some sheaves with some properties, which are defined on stacks using limits, colimits, left-right can extensions. So it's also something that happens in the background. And the notation that we use is F is F. This is bold. This is Laurent series and all this power. And yeah, the objects we will need on one side of this correspondence is XO, which is defined in a standard way, arc space of X and XF with space of X. Question so far? Okay, so let me write a conjecture, and then I will explain everything that appears in this formulation. So, and just even one version of local, unramified, relative. Conjecture says that sheaves on XF over O is quasi-coherent category of quasi-coherent sheaves on G check equivariant quasi-coherent sheaves on M check, but shear. So I will describe this operation on categories in a moment. And maybe maybe one thing that is helpful to look forward to is example where like regular action. So if X is H and G is H cross H, where we invert on one side so that it's spherical. There's probably some involution. So in this case, this is large spherical category. This is in this case we get H4. H is some reductive.
Oh, okay.
So I take two copies, acting on itself. In this case, it will be spherical, and this category is so one factor gives exactly Riemannian, other gives H. Sheaves.
It's kind of H to H.
Say it again.
It's the Hecke category for H, right?
Yeah. And yeah, so like if you know what it is, then shear is what makes it true. So usually what appears is sim G check minus 2 mod check, and so shear is what makes it true. So in this case, we also get this kind of simple equivalence. So so here M check is T star and check. So whatever only check happens, and H check is H check. So one of base goes away, and whatever remains is and check is G star over G check, and that's almost what's written here, but with this star. Functions on G check star, but
Sorry, it's H star mod.
yeah, sorry. Yeah, that's
Yes.
I mean, usually you see G, but yeah, but here it's H. Yeah, any questions about that? Okay, so next we discuss this operation, shearing here. And well, you won't lose much just by thinking about it in this way. So if you have some algebra A, algebra. Okay, well, here it's even like just great algebra, just no things. Then you can make a shear, second degree algebra, and this operation categories is whatever sense A mod to a shear mod. But this is like abstract way to say it. General way without using stake any category of GM action and produce second category of GM action that I will describe.
So shouldn't A have kind of auxiliary grading or something?
A has two gradings, logical and
Yeah, so there's an additional grading.
yes. Plus
It's something that applies to a graded DG algebra. So
yes,
not just an abstract.
And it's exactly what happens here. So you see here, G check star has weight 2, and like if you like if you follow the signs carefully, it will be shearing. We shall discuss in a second. Exactly comes to logical shearing. So let me we will do this shearing in steps. Let's start with graded complexes. Each other, just grab GM, just and we will use seconds. Derived category of GM here. And any object like this can be written as sum of mi, where I is m grading. So each mi is a complex, is a usual complex of vector spaces. Then m shear is defined as a direct sum of mi I. And if one way to draw it should look exactly like this, so that you write your elements using this double degree, cohomological and grading, and if you write a table, then it goes in one of two directions. It seems that it goes in opposite direction, because it shifts left. This is yeah, so it seems that this is direction, but maybe not one of the signs. I mean, this is difficult. This is a definition. So this is kind of corresponds to what happens with this doubly graded object. And this is autoequivalence of GM, where home spaces are graded, where we take homes between ungraded objects. So we take f of all possible graded. And it's moves. And which decomposes as which has grading decomposition. This piece is at I to grading degree. So if you take this full home space, then this is autoequivalence of this category, which satisfies home and shear and shear. I mean, you use some kind of finiteness to decompose. It's the sum of these great pieces. So this is objects and shear on home spaces. You can check it by definition. Change your grading degree, then you have to additionally, like the map that you just wrote, now also has additional homological shift, which is what happens in the element that you wrote before, now has additional homological shift. You can check this exactly. Any questions? Okay, so this is the nicest that here, and it is almost a monoidal autoequivalence. So all so even powers of separation autoequivalences, and with odd powers you add so you go outside of this category. So if you want to differentiate, you define this from red M to red super GM, where the super doesn't do much. You just now have even space and odd space, and whatever happens is just you get additional minus sign when flipping odd spaces. Sorry, but that's monoidal always. It's so it's it also symmetric equivalence for even powers, and for odd powers you get some tricks with signs, because in cohomology you have signs, and you set by spaces where each odd shift also produces a parity. Sum I parity I. Nothing happens with even shifts, and odd shifts you send odd parity so that the signs work out. Then it's some formulas. That's okay. So let's Now let's discuss some other categories, not just array GM. So this will be done in steps, and this is first step. Second is graded category. So for me and category with the module category over this monoid. So module category means that now you can like tensor two elements of two different categories with natural compatibilities, and if you spell out the definition in this case, it just means that apart from T, we reserve T angulated cheap homological shift, then you get additional operation. I guess that's where you really need to distinguish between angulated and TG categories. So all these operations, I guess, work nice for TG categories, work a bit less nice for angulated categories. So that's why you need to do stuff. I mean, think about categories. So this just need to tell what happens when you multiply by a tautological representation. Just have a second total. S just get a second equivalence. Which is quasi. You can multiply by positive powers of cases where torus x is positive powers and its powers of s, or its powers of s inverse and nothing much. So well, and examples of this stuff is graded models, so or equivariant sheaves. So if you have examples quasi-coherent sheaves on some variety Y with G action and M correct is or graded modules over graded algebra. These are the main examples, and yes, here we have structure, and we just so here same objects and shared spaces. So it's kind of what happens here. You can just leave all the objects alone, especially with whole spaces, and it's the same as this. This is what you do, and so another way to think about it is that it's tensor red GM over red GM here, where this action is a bimodule over red GM, where this action is usual right action and left action is sheared in the opposite direction. So Y tensor is old Y. And this expression is defined naturally with minus I here instead of I. Just snapshot is we change module, the right module structure, I guess. So we change module structure over rep GM if you just send object from the right all the way to the left. If old action was something tensor y, then new action is just twist the GM action by shear, and kind of you just change S to ST. And this basis in your home space, then now you have home spaces and all the possible powers of S and T, and now you add them in a different order. List them in a different order. Nothing here.
GM.
Yes. As I didn't tell that, I guess in this definition, you start with like just the usual homes in this category, like the central piece, and then you define full homes as sum over all possible home C X bar small, but if you add all possible shifts, home C X S I T J, you get the space that you need, and this will be auto equivalence with this space of homes, or you can just throw away. It will respect this homological shift if you give powers of S, then these homes in old category are new homes still category. It's kind of what happens when you still have some kind of structure. Any questions? Okay, and now let's so final step is the category that we actually need. So here there are in this right top side there are no grading. Either all. G algebra. And so you have less structure, and here you don't have this kind of shifts and stuff. There is no grade. Shift, your home spaces are ungraded, so you have to do something. Well, I will say what to do. So normally we just consider category the action element gives you auto stuff, and it doesn't work like this. Formal definition is this is model category. Quasi-Gaussian shifts for GM with motion. Where you use multiplication map to tensor forward of box product. GM cross GM. So yeah, this is what is to have GM action, and let me quickly. So examples are the quasi-coherent shifts on Y where now Y just has GM action, but we don't ask the shifts to be correct, or all modules. Is And some like you can write formally and informally you just twist your sheaf. And strategy is to pass to nice objects shear and then pass to all objects. Formally, passing to nice objects is taking well. So there is a monoidal functor like this, which is just push forward. Point. And note that this star structure exactly gives that it's monoidal. Short of tensor product with something else, but here you just tensor product over C. So you have this push forward, and this is functor of monoidal categories. So in particular, that becomes module category order is C, GM, star. I mean, it's like with algebras, if you have a homomorphism of algebras, then the second algebra is module over first. So it's functor to define the tensor action. Tensor by element here using the image. Yeah, so we use this subject to define a subcategory, well, not quite subcategory, so equivariant objects. C, so notation is GM, and definition is of module categories, which define similarly to map of modules as something that should respect the action of this category QC, but with module categories, some of this is not property but a structure. You say how you take out action. Right? C. And well, you can check that this is exactly what you think it is, that this is an object plus like here, for example, that you exactly get equivariant sheaves. Sheaves with additional structure. This additional structure comes from choices that are here in this tensor functors business. So it's in my notes, but it will be. So this is so like we go from one direction. So we start with C. Now we have this CGN, and now we want to go back. So we want to write some kind of joint functor, and that will be inverse for some reason. So how do we do it? Well, we want to make vect into a bimodule, as it happens with modules. Bimodules will give you a joint functors. How do we make vect into bimodule? We take endomorphisms. So, endomorphisms over this QC of vect is, well, GM representations, just what is equivariant object in what is equivariant sheaf on a point. GM representation. It's here. So you have bimodule structure on vect. Yeah. So this one is on the right, this one is on the left. And you use it to write joint pointer. So if you have category D, which is this nice, which is this great category, and category over GM as a product, then you can take less nice category. Yeah. Using right structure, this is a module. I will not say how the product of categories is defined. I guess that's another space where you need DG. Yeah, so I guess in nice cases you indeed you use this to define sharing just here. C share C GM share answer rep M. And you can check that this I didn't like to do in this example. That you start with a mod, you end with a shear mod. Any questions?
So the intermediate step, if I start with like a mod graded, I apply this shearing construction, I get a sheared mod graded, and this so that it's non-graded.
Yes, hopefully. Yeah.
I think that's right.
Well, I mean, there are some theorems there. For some reason, they need category one affines theorem, and yes. So I guess if you try to actually prove it, you get issues at some step. But this is not hard to describe.
It's spelling out some kind of datum that's equivalent to like this category with the GM action is the same thing as like a graded category in the sense that you would usually define it like the humps have gradings.
Yes.
And then this is some other version. The GM equivariant category will be a category of an action about GM, and then the theorem is that these are like somehow.
Yeah. Yes.
So most people call it the equivariant.
Yes. Yeah. That's the word we used. Yeah. I mean, it's kind of mysterious, like that there is an equivalence between categories that are nice and that are slightly less nice, but
it's sort of very clear what's going on if you have a DG algebra, right? And you're talking about A modules, graded A modules, doing shearing to A and stuff. And somehow with C, it's just a relative version. Right. But it kind of comes to that case.
Yeah. Nice that it works. So that's what happens. And now you can, for example, formulate derived geometric Satake while saving space. So you just, I mean, I guess it's a bit. With derived geometric Satake, it's no big deal to write with two shift that appears there, but with this more complicated uncheck object, shrink, and I mean, also I'm writing one of the simplest version, and then they're like, okay, there are two normalizations, you can shear this, shear that, and so it's convenient to be able to quickly write all these changes of logical grading that what I will be telling you is kind of analytic version where objects after taking trace of Frobenius correspond to unitary stuff, and there is also arithmetic organization that I will not talk about at all, that better for reducing that doesn't use additional coefficients. Defined over Z, whatever. Or analogous to the stuff defined over Z. I think, yeah, so that was kind of explanation of why is it why is it important? At least in paper. So let me as promised, let me write derived geometric attack in this way. We have equivalence. Okay. Equivalence of small category of convolution and perfect complexes. Check star is shear over check. And a large category is you see shear of check star or check. So the convenient thing about this notation this normalization choice of grading I'm talking about right now is that there is no action on check. Check has no grading. The action of group check is trivial, so all these cohomological shifts happen only to algebra, but not to the group that is acting in it. So it's a bit nicer to write some things. You don't have to go, full Hopf algebras to create shear on check. So, any questions? So I guess this large sheaves on many equivalent small sheaves. So if you're unhappy with my discussion of small and large categories, that should give you some reference point of what happens, how small and how large these categories are. Let me then start discussing the conjecture that I've already wrote here, which is convenient. So, let me just start discussing equivalences that this equivalence should satisfy. Here. So this category is defined somehow. There is a whole appendix somehow to define. Okay, this is standard. But in a lot of cases, this can be presented in a nice way. Like if it's a vector space, then it's like the limit of vector spaces where you need see lim direct universe of v t minus l t over t m. So this provides you a nicer structure and provides you with a nicer way to define sheaves. So like if you go to full stacks, then you should choose once and for all sheaf or star. Here always use sheaf. So by default, all these things shrink, and you can use only shrink iterations. So sorry. So Schlick pullback and proper push forward, which start just usually it's no difference. And Schlick projection, Schlick phase change, and yeah, in one case, which I will not write out, you have problems. You can do only Schlicks. So start discussing various progresses. This conjecture, so this equivalence is fine. Progresses. This function is noted of x, and here I large category, but similarly to geometric facts like equivalence, you can write a small version, which is small sheaves except it's more perfect indexes over and check here. Versions large and small, and this functor Lx here and here should satisfy several properties. One have distinguished object here and here, and they should that's the structure. That's G-check equivariant. And this is expression we allow. This is push forward of structure sheaf or X O. In Slovakia, this would be point here, just shift point here is not exactly, but it still comes from nice part of this step. There are loops on the arcs. And so this is first property. Other but that will more is Hecke. So there is action of spherical here in derived geometric Sakellaridis, and so both sides of derived geometric Sakellaridis act on both sides of local and unified conjecture, and these actions should correspond to each other. I mean, here H. Just by pricing using performances. or maps of stacks. Stacks, GO, yeah, GO, set, O, set, O over O, where you use second, yes. So like you always diagrams are standard. I forgot this exact one part. Right, section, and here on the inside, so check. You just use moment check to pull back sheaves over G. The G check equivalence is preserved, and this well and shear just pull back. Shearing is pointer on categories. If you have pointer, you see pointer. So you just have pull back from this right side of the direction which is attacking to which this also gives you action of category, and these actions respond I guess I'll yeah, so this is what happens, and I think it's a good time.
Past the hour.
Yeah, so yeah, let me since doing this, let me write this diagram and following the seminar as one question. It's something that happened there when defining multiplication on BFN Coulomb branches. So you take in objects there are different, but you take sheaf here and here. You describe this. So sheaf F balance product with XF mod GO maps to XF mod by right projection, just and the left projection see that you actually use you and also something real in the act, which is not quite, but gives you XF mod. And this is probably different from article part. System here, and then you find the operation as usual, box product of action, pullbacks, and then forward. Yeah. In the first there was additional step of writing everything as GO equivariant sheaves, and then starting with unbalanced product, and then making it forward. Action, which is free. Yeah. So similar and so everything up to this point was quite abstract. So let me I erased exactly one example that I will use, and let me at least start describing it. Start describing what happens in this example, where as promised after this point, and after you don't actually use X from here, just moment map and grazing and stuff. So yeah, so let me continue with. So let me tell a little bit about this category and nice objects in this category that will correspond. So yeah, let me just use objects coming from geometric attack a little bit more. So what I'll use is abelian objects. So reverse sheaves here, which I will not write, and just G check representations here pulled back to this category. So moreover, pull back to N, like nothing interesting happens, you get this G check equivariant. Also, is in graph check, you can do and then shearing. So I like de-sheared this right hand side to just work with usual algebra. So for second, let us leave just in here. Then they generate this term. And the home spaces are relatively nice. Homes, and you just forget about check module structure on the side, and it kind of already nice. Just G homomorphism, E to W, answer O and check. I want you write it in just internal terms and check. So I mean, this is something reasonable, and no higher stuff happens. Yeah. So this is so since I've already so since we are already doing this, so combine pointing and this property. So I just described action of an object of abelian part of the category on this basic object. I take O of M check and I act by this object corresponding to representation of G check. So moral of the story is that if I start with basic object, act on it by static category, then first I generate category, second whole spaces are reasonable. It's not bad. So of course the trick is the hard part is here in the principal group, and here.
How come here right adjoint?
I mean, it's G representations, nothing. I mean, it's not important, but I guess it's I think with vector space you can do some additional stuff if you don't.
As long as W is finite dimensional, which you can
Yes.
assume it's fine, right? The tensoring with W is by adjoint to tensoring with W star. So it's fine.
Yeah, I mean, it's, yeah, I don't know, it's
Kind of symmetric.
from element V, you produce element of W, and then you produce element of O. Check, but, and you can also produce like two elements in the row where this element indexes, yeah. I mean, I didn't.
W finite dimensional, it's Hom V is V star tensor. Oh, wait.
Oh, I think.
Sorry. It should be Hom from W into.
I think for G representative, okay, I mean, it's not something that I will actually use in any form. I won't actually, yeah. I mean, if you don't believe it, I will only write this formula and it's different. But it should be like, I mean, nothing seriously happens with G. Yeah, so let me talk a little bit more about this constructible category. So XO is nice. This is limit of X n, where this is so Xn is X of this important ring. This is inverse limit, and the maps here are good, nice. So X and we assume X is smooth. So X 1 to Xn. These objects are smooth, maps are smooth, and everything is smooth. And 1 in 3, all smooth. Yes, so let me now write something similar for space. Yes, and also the action of GO. So the action of GO on Xn is vectors who action of G of R, sorry, on R points or RT or over T and over Tn. Three nice properties: object smooth, map smooth, and finite dimensional quotient. And we say that, I mean, it is not necessarily true if you go outside of the space. So let me describe how you do it precisely. You include X into V, G, equivariant. Describe the pieces that you inductive limit of the pieces that you use for loop space, just as just what I somewhere. So V F is one, other T T L T over T and T, and in this case of just a vector space, you still have these nice properties. So if you forget about this outer direct limit for a second, then this inverse limit is as nice as it was before. So namely, these pieces are smooth, maps are smooth, and also torsors for unipotent scheme, which is group G same matrix, and action of actually all on these pieces. Like V L vectors finite dimension, which is in this case G of, in this vector case, G of T mod T n plus minus L, if L is negative. So this is very nice. In this case, you can define sheaves about doing that. You just take all the sheaves here on this finite dimensional spaces and then do here, push forward here, and there is no difference between star and Schrieg theory. So, well, at least that's what. That in this case, you don't have to make this choice of star and Schrieg once and for all, and you can do a lot, do more than more. And so we say that X is implicit if this holds for X instead of you can express X as a limit, as this kind of limit. So X is a union of these X cells. Each of these X cells can be as the limit of this nice system of steps. And it's, yes, sorry.
Sorry, is it X or X7 here? Like
X. Oh, we start with X.
Well, X is some function. So I'm considering use of X.
And you say that X is explicit if this happens for X.
Right.
Um,
So it's XF that's written.
Yes. And there is an expectation that this actually always happens in what we consider hyperspherical axis, spherical.
Was this going to be affine or no?
Oh, I see. I mean, I didn't say what to do with quasi, but
I'd like to be able to take it to be Gmod n or something. So when you say quasi-affine, like
yeah, that's exactly what happens in one case with T stars not optional.
maybe G case.
Yeah. I didn't find any like explicit parallels between what happened on the 7 previous talks of this seminar.
I did talk about direct talking last time, so at least.
Yeah. That's true. Yeah, so I mean, it doesn't always happen. Like there is an example that if you take X is zeros of quadratic form, then on the first step you get like non-subjective maps here with jumping dimensions of fibers. So it's some condition, but probably they expect that it holds for X spherical. Yeah, and well, it will happen in the only case we consider when Gm acts for A1. Here things are extremely nice, and have to have some objects that we can and so on. So here, this case is X, L, N, R is just here L is positive again. over Tn. And if you see the here, then and you can describe nice objects here. So let's so delta L is a constant for Excel, which is formally constant K X L N shifted by L with trivial GO action pulled back yeah, where I didn't define the separation, but it kind of comes from the here. This is kind of already shifted constant here on itself, and you can actually do something with these objects. You can compute homes. Right, home delta 1 delta H star G M shift minus something that has cohomology in degrees minus absolute trivial difference and -2, -4, etc. And you can prove it. These objects are Verdier. In this nice shift theories, you also have Verdier duality that you don't have by default with this Schrieg or star choice, and you use it to assume that one of them is less than the other and use full adjunction. Essentially compute some kind of homomorphisms of constant shift. And in which case, this is a definition of derived category of equivalent sheaves. This kind of morphisms by definition. Because the definition is tricky. It's not derived category of equivalent constructible sheaves. It's something else. And this something else gives you exactly this VGN. Any questions?
So can you say this matches up with something on the spectral side, or?
I will. Well, yeah, hopefully it will be. Yeah, it should be here soon. Yes. Yes, and so since we are there is some point about that the action of the category is also cohomologically shifted. So I'll describe only the case. So there is like an additional shift by degree of G, where this comes from a certain character of G that I will not describe, just in the case of Gn is identity. So you, if your element has valuation m, you shift by m, and so like if you have this basic shift in Hecke category for Gn, it this additional shift by m. So yeah, yeah, I didn't follow this shifts precisely, but the upshot should be is that evolution of reverse shift corresponding to nth representation corresponding to G for torus, evolution with delta x should be delta n. Maybe some of these shifts are already appearing here, but that's what should be the end result. And like another consequence of this shift is the corresponding action on functions after a function shift correspondence should be unitary. Take basis of Frobenius sides, they should have the same L2 norm functions on points and check.
That delta x, is that supposed to be delta 0? What is delta?
Yeah, sorry, that.
Oh, I see. It's the same as delta 0.
Yes, yes.
Okay,
yeah.
great.
Here example that is basic object delta x is just delta 0 because that's what you start with. That's what we get on. Sorry.
It's a cheap x though.
There should be omega here, but weird. They okay, well, maybe here for smooth you shift it back so that it becomes. You are using it instead of constant shift in string theories because you don't string theories, but more it's constant shift and in start theory you. Yeah. It's a bit technical, yeah, but yeah, at least something is happening. So like we have some kind of more concrete objects here on the coherent side, spectral side, and here on the automorphic side, at least in this example, there are some concrete shapes. Something happens here. Yeah. So let me go back to pointing just to. Just to get more of this A1 example. So let's just if we have Lx of delta x is OM check. Let us just take endomorphisms on both sides. So on one side we get H star G x in by this derived business. And here, since we're computing G equivalent endomorphisms, it's just a link of invariant functions. This is what is predicted by conjecture. And for example, in derived Satake case, it's computation of it should be standard computation of it should be hopefully it corresponds to Chevalier theorem that G check is categorical is T check mod W, so it expresses G equivalent homology of a point as W invariance of a torus. At least that's what should happen. And yeah, what is happening is in the case when x is A1, Gm, our favorite thing. So H star M A1. Okay, nothing happens here on any A1 homology, so this is just homology of a point. And on the other side, we should take a ring of invariant functions, which is not that bad. So C star M is C star A1. So it's ring of functions is K of xy, where they have weight 1 and -1 with respect to G check. If we take G check invariance, we get K of xy. And now there is grading action with respect to which xy has degree 2. So the homological shift will precisely produce an object in homological degrees minus even integers, even negative integers, positive, which is exactly what happens here. Or maybe I messed up the signs. To science, this is what happens in this example, yeah, which is nice. We see some kind of this equivalence here in this example. Oh yeah, as promised, yeah, I've already talked about business. So now we go to the dual objects in this example. Two acting on a fine space. So let us check what happens. Let us check what happens on the other side. Check what's Vn. So we take Vn and representation, and we have objects Vn and sheaves shear on check and check. Here this is also A1. And yeah, so let me I've told you this is En in Hecke category acting on basic object. So corresponding object on the automorphic side is T n per sheaf convolution with delta, well, 0 in this case, with sheaf at 0 corresponding to delta x basic object. And as we just discussed, this is delta n. So the prediction is that on delta n in this category is on in n. So this is easy to describe. This is home Cn tensor K of xy. This is coordinate ring of M check. This is Vn. This is Vn. And the only only Gn remains here. And well, this is easy to describe. This is so this starts with x n minus n or y n minus n, and then all polynomials in xy. But what happens here is written here on the right board, which is h star gn shift n minus n. Yeah, so this lives in negative homological degrees starting from this one, and this also lives in negative homological degrees starting from this one, just because the grading action has x and y in degree 1. So after shearing, this is exactly what. Any questions about this example? Okay, let me keep all the details in this case and talk a bit about Plancherel algebra. So details are so we should have trig and star isomorphism just because the other side is self-dual, so this predicts that there should be no different star. This happens. There is also Galois story that I'm not talking about, but we started with FQ bar, and like we could have tried to go back to FQ by adding a bunch of Rabini I action and all these operations that I've told you about. So shearing also does take twists, which for us is just changing action of Rabinius. So yeah, this happens, and we are not doing it. Yeah, there is also you can do safe constructible sheaves, which are somehow what happens in geometrical Langlands, that on one side there are. On the other side, you get important singular support. Also not about. And there is also what you can do some kind of additional GM equivariance on both sides and get some statement about Poisson structures responding to each other. Yeah, let me just do some examples. So let me repeat that if x h check. Here we have additional inverse because we are axing one side wrong. We have additional evolution, but evolution coming from somewhere construction. So we get almost derived geometric Satake. You see here. But here we have this additional twist, and here we have -1. So this is derived geometric Satake, but the action of spherical Hecke category is slightly twisted on both sides. So it's additional statement. Geometric Satake plays well with this additional things that appear here because of the construction of this hyperspherical. Yeah. Okay, well, yeah, examples that are also connected to appearing work of this account of Finkelberg and Franklin, Scoria, doing yeah. Only example where not at where M is not a contention bundle is when it's twisted contention bundle by Whittaker character and it's kind of some category of Whittaker. Twisted sheaves on one side and issues on check on another, and this is what came before geometric Satake. Yeah, let me speak a bit about Plancherel algebra. Yeah, this is essentially a way to write O of M check in a very complicated way. So this still appears on the board. So this equation with O is how you can extract it in a categorical way. So if you see here, if you write endomorphisms of basic object, you don't get like readable functions on unchecked. And focus on check. So want something larger. How do you do it? You do internal morphisms of check, where this is tensor category business. So you use that see check no shares here. You check multi-check acts on check. And so for each pair of objects here, there exists an object here in this category defined essentially by this property. This is exactly definition of kernel endomorphism. This is also an object that satisfies whole in kernel whole. Is so it's an abstract tensor category statement that this object or end object exists. Yeah, it can be large, but it's so we use this as a definition. Dual side on side. Well, we should be the same. So define Plancherel algebra of X as internal endomorphisms of these basic objects in spherical in large one. So by this category, as a category, this is algebra object in this category. So it becomes from evolution just this small unit shape and convolution. And this operation should correspond to just usual operations on O of check as O of sim check. This is an algebra object in the category of algebra. Yes, so
you're saying on the spectral side, this is what the center thing is?
This is on automorphic, this is on spectral. They should correspond to each other if we assume the conjecture.
Right. Sorry, I was just saying this last comment. You were saying inner endomorphisms of O of n check is exactly that.
It should be if you prove this conjecture.
But this is just on the spectral side. Just
yeah, this is on spectral. This is on
inner endomorphisms of O of n check is you're saying is O of n check as a symmetry.
Yes, yes,
okay,
yes.
Great.
Yes, and the explanation is because everything responds to each other. Basic object responds to basic object. Action of spherical category responds to action of spherical category. So whatever abstract definition you write, it should be the same on both sides. But it's some non-trivial statement. So it essentially predicts a description of Coulomb branch algebra in the case when your representation is spherical, not in the usual sense, in sense of dense view. So it says like something. Maybe it follows from the definition, but this is like one non-trivial statement. ring object corresponding to branch corresponds to some check, which is somehow constructed from all of this, which is written in paper. Let's just couple if we so in this like nice case, we can try to compute isotypic components. Well, what would be isotypic components for projection? But here is just homomorphism from representation corresponds to homomorphism from sheaf supported on a single point. This menu. Which is just action. Yeah, I mean, this is exactly what we want. Components is morphism from representation. Went by X in spherical category on basic option. Yeah, sorry, this is just definition. This is just definition. It's fine. And we can write stuff to services. Delta J, delta 0, which is have understanding of cohomology of this object PLX. So for each isotypic component G, it lives in X minus J, and so on. So kind of a triangle on. And it's connected to Braverman-Finkelberg-Nakajima. Computation similar to this one. So how to describe isotypic this object. Main thing is that this is an object on BFM business, and similarly here you can define variety of triples just the same. Well, specify the product itself. Here this is exactly the BFM. And then, so like the upshot is you do stuff on R. So this is some finite dimensional approximation of a pullback of constant sheaf. This is pullback of this sheaf on Braverman under this projection. So like this, after some more work, this connects ELX to defend Coulomb branch algebra. And in case of representation, this PLX is the ring object in the spherical Hecke category, which and Similar object was constructed by BFN in one of the papers after the main one. With quivers and strings paper, and this is exactly the object that appears as a link object in spherical category. So this is some kind of realization object in certain direction where he would require but allow any so thank you.
Are there any questions?
For isotopy case, I think this is exactly the slight crucial calculation in Ginsburg's that I did before in my talk that goes in. Yes, same with this thing is in the isotopy case, it's energy check. Because the G check and variance are like variance, but if you do this kind of inner
Again?